Thousands of years ago, the Greeks and Egyptians adopted the human foot as the first known unit of measure. But whose foot should set the standard? King Henry I declared that a yard should be defined as the distance from the tip of his nose to the end of his thumb. The invention of the metric system in 1790 improved matters somewhat by basing units of measure on more widely agreed upon standards, like the circumference of the Earth. Back at the turn of this century, Lord Kelvin, namesake of the International Temperature Standard, said it best: "One has but a poor understanding of that which one cannot measure." Today, we try to have rational, simple, and consistent measurement systems based on sound scientific principles. The goal of this video series is to introduce you to the principles of measurement, but we will also show you some of the standard techniques and equipment. The series is designed as a basic introduction to measurement. It should help you whether you are attempting to learn about measurement as training for a new job or you're trying to solve a particular measurement problem. The series may not give you all the answers, but after watching, I hope that you will at least be able to ask the right questions. I've come to the NOAA research vessel Albatross 4 at its home port in Woods Hole, Massachusetts to talk about fluid quantity and flow measurement. The Albatross actually has a long history of innovation. The original Albatross was in fact the first vessel or ship ever to have onboard electrical power, and the light bulbs in that ship were installed by Thomas Edison himself. Now, the current mission of the Albatross is oceanographic research, and it's a good site to talk about fluid quantity and flow measurement techniques. Liquids and gases are both fluids, and we can use similar techniques to measure both. This is an example of a small handheld anemometer, which uses a small propeller to measure airflow. As air flows through the device, it spins the propeller and gives you a readout here. Now, a similar technique is used in one of the experiments here on the Albatross. This is a set of plankton nets, which are called bongos by the scientists, and they're used to measure the density of plankton at different levels in the ocean. The way they're used is that the nets are towed through the ocean for a fixed period of time, and plankton is collected in the back of the nets. In order to know what the density is, you need to know how much water you pulled the nets through. So we have a flow sensor here in the throat of the net, which measures the flow through the net. I have an example of one of the flow sensors here. And you can see, again, the way it works is that as water flows by the device, it spins a small propeller here. Actually, it spins this way. And the number changes every time the propeller goes around. Then what we do is we've calibrated the device so we know what the integrated flow rate is, or integrated flow. So this is used to calculate how much water has actually gone into the net. Now what I'd like to do is go up to the bridge and talk about some techniques to measure the quantity of liquids. Let's start talking about the measurement of quantities of fluid. Now, quantity is really mass. However, here on the Albatross, we measure the quantity of fuel on board the vessel in units of gallons, which is a measurement of volume. Now, this is commonly done, and the mass of the fuel can be related to the volume through the density. mass is equal to volume times density. So this works well as long as we know the density of the fuel or fluid we're trying to measure. However, if the fuel temperature changes, the fuel will actually, if say we heat it up, the fuel will expand and change the calibration between mass and volume. So you'll sometimes see quantities of liquids reported in volume units, say gallons or liters or other volume units like a cup of fluid. And you also see quantities of fluid sometimes reported in mass units, either kilograms or pounds. Because gases can be compressed, we can't use volume techniques to measure the quantity of the gas. So in fact, we use the fact that they're compressible to measure their quantity. In this scuba tank here, the mass actually does change when I fill up the tank. So if it was full, it would sink in the ocean here, and if it was empty, it would float. But I need a more accurate method. Now what I do is actually use the relationship between pressure and mass. If this were an ideal gas in the tank, the pressure times the volume of the tank is equal to the mass of gas in the tank times the temperature times a calibration constant. So that's actually what I do. And in fact, if you look on the regulator, there's a small pressure gauge. And I've pressurized it. There's about 900 pounds per square inch of pressure in the tank. Because the maximum amount of pressure in the tank is 3,000 pounds per square inch, you can see that this tank is actually almost empty. One simple method for measuring the quantity of the liquid is by the use of calibrated volume techniques. I have here a couple of simple examples. This is just a measuring cup, which has got calibrated volume. This is a graduated cylinder, and this is a calibrated beaker. Now, the way you make the measurement, say, on this graduated cylinder is by looking at the height of the column of fluid, and you can see that there are measurement marks. This particular cylinder is calibrated in milliliters. Now, you can run into some problems with the measurement. For example, if you look very closely at the boundary between the liquid and the air, you can see that the fluid tends to run up the side of the cylinder due to the surface tension, or what we call the meniscus. So you actually make the measurement at the flat part of the fluid, and you have a small error due to the meniscus. Now, if we were to try to use this cylinder on a moving vessel like the Albatross here when we're at sea, you'd run into a problem. If you look over my shoulder, you can see there's an inclinometer that shows that the ship will have a tendency to roll and pitch. The inclinometer is calibrated up to 50 degrees, but it would be very actually dangerous if we went over that far. But it's not uncommon to roll, say, 10 degrees. Now, if I look at the cylinder and roll it 10 degrees, left and right, you can see that it becomes unclear as to what the measurement is. The measurement's ambiguous, so I either have to sort of average the measurement or tilt the cylinder to level out the fluid again. Another thing that can happen in a moving vessel like a ship or a helicopter is the shaking of the vessel. The vibrations can cause sloshing of the fluid, making a difficulty in making the measurement. Now, for smaller volumes, I can use a similar technique. This is a pipette. What I can do is I can draw a fixed amount of fluid up out of the pipette. Okay. This particular one, again, is calibrated in milliliters. Okay. And you can see I actually have a problem because I got a little bubble that went up into the pipette. So that bubble will create an error in the measurement. And let me demonstrate that a different way. Let me just get the fluid out of here. If I use the graduated cylinder and now make a measurement of a more difficult fluid, let's take this Coke here and pour it in the cylinder, you can see I run into another problem. Okay, if I fill the cylinder with Coke, what you can see now is that I obviously have a lot of bubbles in the fluid, and the measurement is ambiguous. I can't See, if I just look at the brown fluid right now, you can see that it's changing because liquid which is trapped up in the bubbles is slowly dropping down into the solid part of the fluid, or total part of the fluid. This is an example of what we call a multi-phase problem, where I have some of the fluid is liquid, but some of the fluid that I'm trying to measure was also in there as gas, okay? And it becomes difficult to make that kind of measurement. Fuel and water are the two most important quantities that are monitored on board the ship. However, it's interesting to note that there are no fuel gauges or water gauges here on the bridge. Those quantities are actually monitored below decks. I've come 2 levels below the bridge to the top of the fuel tanks to show you how fuel is actually measured on board the Albatross. The way it's done is much like the way you would measure the oil in your car. What we actually do is come to several of these what are called sounding ports to dip the tanks. These are 2 for the forward fuel tanks, the port and starboard tank. So if I just show you, what I do here is take this tape measure with a weight on it and put it down into the sounding port all the way down into the tank. When I reel it up, what I'd see is that the fluid would have wet the tape measure at some point. And there are sounding tables which convert the height of the fluid to the amount of fuel that are actually in the tank. There are different sounding tables for each tank because their geometries are different. We're now 4 levels below the bridge in the lower engine room. And I've come here to show you an example of a very simple level gauge. Behind this wall up here is the hydraulic fluid storage tank on the ship. And this is a simple site level gauge. It's simply connected into the tank at the bottom and top of the tank. And you can see that the level of fluid in the tank is monitored right here. So in fact, the level of fluid in the tank is right back behind us here. So that the crew can monitor the level of hydraulic oil. Now, this gauge isn't calibrated, and in fact it's not necessary. They've just put some marks on here to know where the normal oil level should be. You can also measure the quantity of fluid in a tank using a simple float system. This is a simple fuel gauge where this cork float rises up and down with the level of fuel in the tank and is displayed on a calibrated gauge here. Actually, this is an uncalibrated gauge because it doesn't have any numbers on it. The same technique can be used in a very simple closed-loop control system to maintain the level of fluid in a tank. The float is connected to a switch. If the float goes too low, that switch opens and allows more fluid to come into the tank. If it gets high enough, it shuts off the switch. And you can probably actually see this in the toilet in a bathroom in your house. One electrical technique that we use to measure fluid quantity is a capacitive technique. Now, the capacitance between 2 electrodes is dependent both on the dimensions of the electrodes, both their length, their width, and their separation, and what's in between the 2 electrodes. So, for example, if we have air between the 2 electrodes, it will have 1 capacitance. If we put a material like fuel or water between the electrodes with a different dielectric permeativity, that will change the capacitance between the 2 plates. We can use this principle by putting those plates down into a fuel tank or some other liquid tank. And if we know the dielectric permeativity of the liquid, as the tank fills, the capacitance of the gauge will change. Now this actually turns out to be a very nice technique for fuel gauges, particularly in aircraft, because the change in permeativity with temperature is about the same as the change in density of the fuel with temperature. So this can be calibrated to effectively be a mass gauge. Now, we run into a little bit of a problem with aircraft fuel tanks because the fuel is normally stored in the wings, and as you go out to the tip of the wing, the fuel tank gets smaller. And the way we actually adjust for this is we put several capacitive gauges in the tank, and we adjust their dimension so they're effectively weighted by the dimension of the tank at the measurement location. So essentially we've calibrated out that non-uniform tank geometry. Another technique which is used for fluid quantity gauging is an acoustic technique, which is similar to the sonar and depth finder on the ship here. Now, if you look at the display from this depth finder, there's actually two scales here. One is a very large scale and one's a small scale. If we look at the bottom, what you're actually seeing are the echoes from the bottom of the harbor, which are about 3 meters below us. And in fact, you can also use this to find fish. You'll sometimes reflect off the fish. The way this works is an acoustic transducer in the bottom of the ship transmits a pulse down into the water. It travels to the bottom of the harbor and is bounced off the mud at the bottom of the harbor, reflects back and is picked up by another transducer in the bottom of the ship. By knowing the time between when we transmitted the original ping and when we received the return echo, we can infer the depth of the bottom of the harbor if we know the speed of sound in water. The distance is essentially the round-trip time times the speed of sound divided by 2 because it was the out and return time. We can use the same technique. We would put a transducer in the bottom of the tank and have it transmit the acoustic wave up into the fluid, and the wave would be reflected from the air-fluid interface and again be returned to the transducer at the bottom of the tank. By again knowing the round-trip time and the speed of sound in this fluid, we can then figure out the depth of the fluid. Now this has a little bit of a problem in that the speed of sound depends on the temperature of the fluid, so we may have to also monitor the temperature of the fluid. We can use the same technique in sort of a different way if we were to put an ultrasonic or acoustic transducer on the top of the tank, reflect and send the signal from the air, reflect again off the air-liquid interface, and use a pickup on the top of the tank. This has the advantage that you can use it for materials where the acoustic wave may not propagate. So, for example, you could use it for grain or for sand. And we looked at one of these transducers when we were at the Omega Engineering Labs. I have here an example of an ultrasonic level sensor. In what I have here is the transducer, which then sends a wave down into a tank. And normally this is used in a very large tank. The ultrasonic wave reflects off of the surface of the fluid or grain or whatever material you have in the tank and is reflected back to the transducer, which picks up the return pulse. By knowing the time it takes the pulse to go down to the free surface and back, you can figure out how much fluid you have in the system. There are many different techniques that can be used to measure fluid flow, and I'd like to first talk about those techniques which are commonly used in constrained systems such as pipes. Now, in a constrained system, you don't need to know about the direction of flow. All you really need to know is the magnitude. One common technique that's used in fluid delivery systems such as gas pumps or this oil pump here in the engine room of the Albatross is a positive displacement flow meter. And there's a positive displacement flow meter right down here in this system. Now, conceptually, the way a positive displacement flow meter works is to count fixed volumes of fluid that go through the flow meter. So you can think of it as filling up this bucket, pouring it out, filling it up again. If you know the volume of the bucket and you know the number of times you filled it up, you know the total flow that's gone through the system. Now, actually, the way this one works is that flow goes through this meter. As the flow goes through, the fluid actually, in fixed volumes, pushes through a mechanism, effectively a cam, and as it pushes through, it turns the mechanism up in the gauge here, and you actually get a count of the number of fixed volumes that have gone through the system. This is a very nice technique in that it's a mechanical technique. However, it has the disadvantage that there's a fairly high pressure drop across the meter. So as a result, it's really normally only used at the end of fluid delivery systems where you're going from a fairly high pressure inside the pipes out to a tank or something like that where the pressure is very low. One of the most common techniques for measuring flow rate in industrial applications is a differential pressure technique. Now essentially what this is you put a blockage in a pipe and measure the difference in pressure before and after the blockage. If the blockage is appropriately designed for the fluid viscosity, flow rate, and density, then what you'll get is a pressure difference which is proportional to the square of the flow rate. Now the blockage can be a simple plate placed in a pipe flange with a hole in the plate, or it can be more sophisticated designs such as a nozzle or something that we call a venturi. Now what a venturi is a restriction in the flow. What I do is I do a restriction, typically this is about 22 degrees, to a straight section of the pipe, and then a slow expansion back to the original pipe diameter. The pressure is measured before the venturi and at the constricted region. Now the advantage of a venturi is that it doesn't cause as much pressure drop as a simpler device such as a simple orifice. These differential pressure techniques are very nice in that there are no moving parts, so they're very reliable and fairly inexpensive. The disadvantage is that they typically have a limited dynamic range or range of flow rates where they're accurate, and they cause a pressure loss in the system. Another type of device which uses blockage to measure flow rate is the variable area flow meter, or sometimes called rotometer. And what this consists of is a tapered tube with a float in the tube. The flow causes a pressure force on the float, which is balanced by the gravitational force. Now we looked at several variable area flow meters when we were at the Omega Engineering Labs. One way to measure flow is with a variable area flow meter. In a variable area flow meter, there's a tube which is narrower at the bottom and wider at the top. As the flow goes up through the tube, it pushes on a float, and some of the fluid leaks by the float. As the flow rate increases, it pushes the float higher and higher in the tube. This is a large unit designed to be used for some sort of fluid. We also have a smaller unit also for use with fluid. And you can see here, again, the wider tube at the top and narrower tube at the bottom. And you can see there's a silver float in here. Now, I've hooked up a unit here that's a gas unit, and I'm going to turn on the air here. And you can see, as I turn on the air, the float, which in this case is a silver metal ball, will move up in the tube. Let me increase the flow rate a little bit more. And here we go. As the flow rate increases, you can see that the ball will reach a stable point, at this point around 40 cubic centimeters a minute. I have here some examples of some rotary flow meters. This is a very large flow meter that's designed for use in large pipes with liquids. And what happens is, as the fluid flows down the pipe, it spins this little propeller in here. And as the blades of the propeller go by a Hall effect sensor, or it could be an optical pickup, it creates a pulse. And what you do is you actually calibrate the flow rate to the number of pulses coming through the system. Now, this one's designed for use with liquid. This is a smaller one that's designed for use with either liquid or gas. And you can see if I blow into it, it'll cause the propeller or rotary vane to spin. Turbine meters can be very accurate, but they have the disadvantage that they normally cause a fairly high pressure loss in the pipe. They also need to be mounted in a straight section of the pipe to avoid errors in the measurement due to turbulence or swirl in the flow. Now there's a related type of flow measurement device called a paddle wheel sensor that we also looked at the Omega Engineering Labs, and we'll go see those now. Here are two examples of paddle wheel type flow sensors. The way a paddle wheel sensor works is the flow causes rotation of the paddle wheel, or in this case an optical pickup with a light sensor. I'm going to take this unit and put it into this flow system I have here. And when we turn on the flow system, the rotation of the paddle wheel causes the pulsing of the red light in your picture, which is the interruption of the optical fiber. That can be calibrated with flow rate depending on the fluid you're using. When a bluff body is exposed to a flow, you'll get vortices, which are effectively small whirlpools, shed off the back end of the body, first on one side and then on the other. Now, you may have observed this phenomena if you've ever canoed. As you drive a canoe paddle through the water, you'll see small vortices shed off of either side of the canoe paddle. Now, the frequency of shedding of these vortices is related to the flow velocity, and we looked at a vortex shedding flow meter at Omega, which uses this principle. This is an example of a vortex shedding flow meter. The flow causes vortices to be shed off this vortex generator, which you can see here in the tube. The vortex shedding frequency is related to the flow rate in the shedding of the vortices is picked up by an optical sensor located in the vortex generator. There are several acoustic techniques we can use to measure flow velocity. One technique, called the time of flight technique, uses the difference in the speed of the wave as it goes downstream in a flow system compared with going upstream. Because the acoustic wave will go faster as it gets carried along with the flow, we can then infer flow velocity by comparing a wave sent upstream with a wave sent downstream. Another technique we can use to measure flow velocity is a Doppler acoustic technique. And you're probably familiar with the Doppler effect. That's the phenomena that causes the tone of a siren to change as a vehicle goes by you. As the vehicle approaches, the siren will sound higher in pitch, and as it goes away, it'll sound lower in pitch. Now, the percentage and change of frequency is simply the ratio of the speed of approach divided by the speed of the wave. Now, this effect is used in the ship to measure speed through the water in these Doppler speed logs that you can see behind me. The way this works is we send acoustic waves out from the bottom of the ship. One is sent looking forward, another is actually sent looking out to the side. We accurately know the frequency of the wave that goes out. And what we do is we compare that to the wave that's bounced back at us, either off the bottom or things in the water, small particles in the water. By comparing the two frequencies, we get a measured Doppler shift. And by knowing the angle of the beam that we sent out, we can figure out the speed of the either boat through the water, or in this case, since we're tied up at the dock, we're simply looking at the speed of the current underneath us. So you can see right now that there's about a 1 knot current coming from the left and about a little greater than 1 knot current coming from the bow of the ship. Now I'd like to talk about a few of the techniques that are used for measuring the flow of air or a gas. You can probably see behind me several of the anemometers that are used on this ship. Now, for airflow, we need to measure both the magnitude and direction of the flow. So these propeller-based anemometers actually rotate to give you the direction of flow, and the propeller rotation gives you the magnitude of the flow. Now, wind speed and direction is a critical measurement for meteorological applications. And we went up to the Mount Washington Observatory, which was the location of the highest wind speed ever recorded by man, to see how wind direction and flow is measured there. I'm standing on the instrumentation platform at the top of the Mount Washington Observatory. You may be able to hear there's a little bit of wind up here, but it's actually a fairly calm day. I'm surrounded by a variety of anemometers, several rotating vane anemometers over here, a rotating cup anemometer over here. Also, during the winter, you need a heated system because ice forms on the anemometer. So if you look up here, you can see there's a heated pitot system. When we were up at the Mount Washington Observatory, we saw several pitot tubes that were used for wind velocity measurement. Now, the pitot tube is commonly used for airspeed measurement both in wind tunnels and on aircraft. And what I'd like to do now is go back to MIT to one of the wind tunnels to see how a pitot tube works, and then go out to the MIT flight test facility to look at the mounting of a pitot tube on one of the flight test aircraft. I'm standing in the test section of one of the wind tunnels at MIT, where students conduct a variety of experiments, such as testing the aerodynamic performance of airfoils or sometimes measuring the drag of bicyclists or skiers. Now, you can probably see that the wind is coming over my shoulder and sort of blowing through this open jet test section. And the wind's blowing about 40 to 50 miles an hour right here. Now I'll step out of the airstream. And I'm going to shut off the tunnel here. When we make measurements in the wind tunnel, we need to know the wind velocity very accurately in order to be able to use the measurements that we get. Now, in order to do that, we typically use a pitot tube. And the way the pitot tube works is it measures the difference in pressure between the front of the tube and the side of the tube. You can see there's a small hole here which goes to a connection at the bottom of the tube. In fact, the static measurement goes to this other connection. Now, as this is exposed to the flow, what happens is that the pressure in the front of the tube, what we call the total pressure, is higher than the side pressure, and that difference is proportional to the square of the flow velocity. We've seen pitot tubes used for flow measurement at the Mount Washington Observatory, but we can also use a pitot tube to measure the velocity or airspeed of an airplane. In this particular application, you can see that the pitot tube, which measures dynamic pressure at the head, is located slightly away from the body of the aircraft so that it's cleanly exposed to the flow. In addition, this particular pitot tube is heated so that if the airplane flies through icing conditions, say, the probe will remain clear. Another phenomena that I can use to measure flow velocity is convective cooling. An old sailing trick is to lick your finger to measure the flow velocity. And the principle here is that the air blowing by my finger causes evaporation, which I can feel as cooling on my finger. Now, the same principle is used in hot wire anemometry or hot film anemometry. And we'll go back to the wind tunnel at MIT to look at this technique. Another method we can use to measure flow velocity is by looking at the effect that the airflow has on cooling or the thermal properties of a probe. So this is an example of what we call a hot wire probe. And basically the way it works is the air flowing by this thin element at a constant temperature by running current through it. And by knowing the calibration of the device, we can infer what the flow velocity is by how much current we need to put into the element to keep it at a constant temperature. Now, these are very sensitive devices. I have another one here hooked up to this meter, and you can see that just my breath can cause it to sense a scale of full-scale deflection. So we can take the probe and actually put it into the airflow, which is running fairly slowly here, and you can see that I get a fairly accurate measurement. And you can see that it responds fairly quickly when I take it out of the flow. The speed of response will depend on the size of the wire. A very fine wire will have a fast response, but will also be very fragile and tend to break if the flow is too high or if it hits a little piece of dust or something like that. Often we can learn much about flow by just visualizing the direction of the flow or flow patterns. Sailors often tell a lot about the wind just by looking at the ripples in the water. There are many different techniques for flow visualization, and what I'd like to do now is just go back to the wind tunnel at MIT to look at just a few. In addition to knowing the velocity of a flow, we're often interested in knowing the direction of the flow or some other aspects of the flow. So for example, we'll use a smoke wand to see how the air flows around this airfoil, and you can see that near the tip we get rotation in the flow due to what we call a wingtip vortex. And as I go through here, you can see turbulence which is created by the flap there. Another flow visualization technique is to tuff the airfoil or body that you're interested in. So So in this case, we put these red tufts on the airfoil, and you can see that the flow is fairly clean and going straight back on the airfoil. Now as I increase the angle of attack of the airfoil, you can now see that the flow doesn't go over the airfoil very cleanly, and we have what we call separation or turbulent flow. Okay. As I reduce the angle of attack of the airfoil, you can see that the flow smooths out again. So this is another flow visualization technique that we use. One of the most sophisticated techniques for both visualizing and measuring complex flow patterns is the laser Doppler velocimeter, or LDV. I've come here to the water tunnel in the MIT Ocean Engineering Department to look at a two-component LDV system. Right now, the tunnel is set up to look at the flow patterns in the wake of a propeller. And the water tunnel pushes water in this direction, and you can see that the LDV is set up behind the propeller. Now, there are two sets of beams here. You can see a blue set of beams and a green set of beams. The blue beams are set up to measure flow in the horizontal direction, or the mean direction of flow in the tunnel. And the green set of beams are set up to measure the component of flow in the vertical direction. The actual measurement point is where all the beams intersect. You can see the beams cross here. And the laser can be moved in, out, up, and down to adjust the measurement location behind the propeller. Now, to show you how an LDV works, what I'm going to do is shut off the green set of beams and just look at the horizontal measurement. The laser Doppler velocimetry technique is similar to the acoustic technique we talked about a little while ago. However, this time, instead of scattering sound waves, particles in the flow scatter light from the lasers. Now, recall that the Doppler effect is caused by motion of a source or scatterer, and as this source approaches the receiver, the Doppler shift will cause an increase in the frequency. As the source moves away from the receiver, the Doppler effect will cause a decrease in frequency. And so what we do, if you look at the two beams here, we have one beam which is looking slightly upstream into the flow, and another beam which is looking slightly downstream. The upstream beam will see particles approaching it, and scattered light will have an increase in frequency. The downstream beam will see particles going away from it, and will have a slight decrease in frequency. What we actually do in this heterodyne system, which means we're comparing the two scattered light beams, is that we compare the upshifted frequency from one light source with the downshifted frequency from the other light source. And as the velocity increases, the shift in frequencies will increase also. So we have a very sensitive way to measure velocity. Before I show you the processed LDV data, I wanted to show you the raw data coming in from the laser system. If you look at this oscilloscope, you can see the output from the photodetector, and every time a particle passes through the measurement zone, you can see a little burst on the oscilloscope. So each of these bursts is a particle that we're measuring. Now if I turn on the tunnel, turn up the speed here, and look at this computer, what it's showing is essentially a histogram of the velocity of the last 400 particles that the LDV system has measured. Now remember, we're only looking at the blue laser beams, which were measuring the flow, the horizontal flow along the tunnel. So because I just sped it up, you can see that the velocity increased. This is a nice narrow velocity distribution, which indicates that the flow is fairly smooth and laminar. If there was turbulence in the flow, you would get a spreading of the velocity distribution because some particles would be going faster or slower than the mean value. Now, if I increase the speed again, you can see what happens is the LDV system starts to count some of these faster particles. The distribution will shift, and again, we should get a nice narrow distribution at the higher value. Now remember, this is only looking at one component of velocity. If we were to turn on the green laser system, we would be able to measure a second component of velocity in the vertical direction. And if we were to add a third laser system, we could measure all three components of velocity. So depending on your particular application, you may want to measure 1, 2, or 3 components of velocity using an LDV system. I hope by now you appreciate that there are many different techniques for measuring fluid quantity and flow, ranging from the simple, crude, but reliable techniques of sounding fuel tanks using a tape measure to the more sophisticated techniques of laser Doppler velocimetry. Now, the technique that will be right for your application will depend on your particular measurement requirements and the physical properties of the fluid.